Alrighty, let's call this a stable number of participants. Welcome everybody to this research track session number 2. So this is all about time and predictions. And as you will see, or as you have noticed already, we have 3 papers that actually are very nice. Well, not only in terms of content, we will see about that in a second, but also nice in terms of fit together because they somehow indeed are closely related. Of course, different topics, different problems, different approaches, but I think it very nicely fits together. So this is a very nice session, I think, in terms of the topics covered, because yes, the papers indeed target different aspects that are related when it comes to analyzing performance of processes. So it's my pleasure now to first hand over to Sarah. She's with the University of Technology in Eindhoven, and that is also where her co-authors come from, except one, if I count this correctly, but she will, I think, mention that as well. And this is about detecting system-level behavior leading to dynamic bottlenecks. Sarah, please go ahead.
Yeah, thank you, Matthias, for the introduction. So I'm gonna share my screen at first. And you can see my screen, right? Good afternoon, everyone. I'm Zahra Tusinejad, PhD student at Eindhoven University of Technology. I want to present our work, detecting system-level behavior leading to dynamic bottlenecks. So let's start. And we do our project with Vanderlande. Vanderlande is a company which has baggage handling system in different airports. Now, let's follow a story so I can show you what's the motivation for our research. So if we imagine you have a flight which leaves at 10:40, and they ask you to check in before 10, but you check in your bag at 10:15. Now, if when your bag is in the system, a dynamic bottleneck happens at 10:30, and it causes delay of 10 minutes, then as a result, your bag will leave the system at 10:45, which means the bag misses the flight. Now, let's have a look what happens inside such a baggage handling system. Here is a simple example of a baggage handler. We see bag number 1 moves from location 2 to location 3, and bag 2 moves from location 1 to location 2. Some seconds later, we have 2 more new bags, bag 3 and 4. And when bag 5 arrives to the system, we stop the bag in the segment between location L1 and L2 is higher than above average of the load on the segment. So we call this situation a high load. Now, after some seconds, we can see that bags 2, 3, 4, and 5 move forward through the system. And we also have 3 new bags, bags 6, 7, and 8. At this moment, when bags 2, 3, 4, and 5 are between location L2 and L3, again, we have the same situation as we had before for location L1 and L2. So high load here. Now, some seconds later, again, we see all the bags move through the system. And when bags 2, 3, and 4, and also 5 are on the same segment, as you can see here, the segment between location L3 and L4, again, we have the same situation and we have a high load. And you can see how high load propagates through the system. In the next time slide, you can see that bags 2, 3, 4, and 5 move forward together. And again, we have a high load on the segment between location L4 and L5. So, and which means we have too many bags on location L4 and L5. And we should, if we look at the picture, we can see that there is no capacity for other bags on this segment. And so L4 cannot process another bags. But we also see that we have bags 6, 7, and 8 between location L3 and L4. These cases between L3 and L4 are stuck for 2 more minutes. And we should also know that the conveyor belt between L3 and L4 is not continuous. So the bags can still enter through L3, but they cannot reach L4 because the conveyor just in front of L4 stopped. So we call this situation a blockage. And a blockage is a dynamic bottleneck. Now, let's look at our research question. So the first research question is, can we detect dynamic bottlenecks? But we should know dynamic bottlenecks involve many cases. So they happen at system level. So as a result, the question will be, can we detect system level events? And dynamic bottlenecks exist and they are in the system. So either if we want to predict them or prevent them, we need to answer 2 more questions. The first question is, can we detect what system level events precede dynamic bottlenecks? And the next question is, are there frequent patterns before dynamic bottlenecks? What you see here is we call it performance spectrum. And you can see 5 timelines. Now, let me add a trace for case number 1. Each time that we have a case on a specific location, we have a case level event. This type of events are like a normal event in a data. So it has case ID, it has location, and also time. We call such line between 2 case level event a segment level event. Now, I want to add 4 more bags 2, 3, 4, and 5. And you can see these 4 bags are close together, which means, for example, we have a high load between location L4 and L5 here. We call this high load a system level event. And you can see the situation of the system at this picture. Now I will add 3 more bags. You can see that these 3 bags are stuck between location L3 and L4. So we have a blockage here. The blockage also is a system level event. And you can see the situation of the system at time T1 at this picture also. And this is a real example of performance spectrum on real data. And in the paper, in the event data model, events are ordered by cause-effect relations. And we have hierarchy definition, case level events, segment level events, and finally system level events. We have a framework to detect system level events as groups of segment level events. So we detect 2 types of system level events, which are high load and blockage. Now let's have a look at different steps in our method. So the first step is segment level event detection. After we detect the segment level event, we detect the system level events, which are blockage and high load. These 2 steps are related to our first research question. After we detect system level events, we detect the relation between them, and then we detect cascade of system level events. These 2 steps are related to our second research. And after we detect the cascade of system level events, we apply a frequent subgraph mining method to detect frequent subgraphs. And this last step is related to our third research question. Now that we detect system level events, which are blockage and high load, we encode them as a node. For example, for a high load, we encode it as a node like this. So we have start location, end location, a start time, end time, and also we have the type of system level events. We can encode a blockage also as a node like a high load. We say 2 system level events are related if and they overlap in time. Then we draw an edge from the system level event that happened at first to the system level event that happened later. Now, how we detect the cascade of system level events? If you look at this picture, you can see we have 5 system level events, A, B, C, D, and E. And we have one node for each one of them. Now, if you look at two system level events, A and B, you can see that they overlap in location L3 and they overlap in time. So we draw an edge from A to B. For the same reason, we draw an edge from B to C, C to D, C to E, and also from B to D. We call such a graph a cascade of system level events. Now that we detect the cascade of system level events, we apply a frequent subgraph mining method and we detect this type of pattern. In the top of the pattern, you can see the frequent subgraph, the context where the subgraph occurs. Now, for the evaluation, we use an event log from log, and we found 41 to 151 blockages per day with delays up to 8 minutes involving up to 13 backs. And we found 586 to 1,090 cascades per day, and 23 to 56 cascades include at least one blockage. And we detected 500 frequent patterns that lead to a blockage with 4 different patterns, like forward propagation or backward propagation. In the validated discovered pattern, each edge matches dynamics of baggage handling system, and pattern capture how the system works. And you can see more detail in the paper. And now, as a conclusion, we detect cascade of system level events that lead to dynamic bottlenecks, and our method works on real-life European airports. The code also is available. And for our future work, we want to generalize the method and make it more powerful, and we want to use the pattern for prediction. And that's it. Thanks for your attention.
Thank you. Thank you very much. So now we have time for questions. So I would like to invite everybody to, well, either raise their hand so that I can unmute them, at least try to do so that they can pose a question, or also use a Q&A functionality and pose a question there, or also indicate that you got a question. You may also indicate that there. So while everybody, oh no, there we have the first one. Vadim. And now David, can you help me with the unmuting? So while we'll try to figure that out,
Yes. I can.
Okay.
I can do it.
Yes. Could you please? Because apparently.
So, Vadim, you can speak, I think.
Can you hear me?
Yes.
Yes.
Ida, thank you for the very interesting presentation. I have a question.
Yes.
If your approach can be applied to other types of business processes?
Yes. To be honest, we didn't apply that, but it's actually part of our future work. So we just applied that on baggage handling system, but it's our aim, and it seems that it should work for other processes, for other type of data also. So based on your type of the data, based on your system or any type of the data you want to apply. So anyway, you can have different type of system level events, and again, the system level event usually can be related. So yeah, I think it should be applicable.
Thank you.
Thank you for your question.
Maybe if I can just follow up on that one. Bart Holmes, I saw the question in the chat. I'll get to that in a second. So in your approach, you have those three different levels, right? The cases, the segments, and then the system level events. And well, you start with a log where there is a notion of a case, right?
Yeah.
Now we know that this may be sometimes also subject to, well, the definition, right? We may, given some event data, right, there may be different notions of a case that are of interest. So on the one hand, you have this notion given at what constitutes a case, but then on the next level, when you need to group segments, right, this is not given, and you need to find mine correlations, right? So I was wondering, because in this first step, you have this partitioning or this grouping given. In the second step, you actually mine this via correlation analysis. So can't you then also apply this to a context where you don't have this notion of a case given? Because essentially what you do on the second step, this correlation analysis, you already apply on the first step. Would that be something that makes sense?
Okay, so yeah, in a way that if I realize completely your question, so yes, we have two steps of detecting correlation. So the last step is detecting the correlation between just system level events. But system level events are a group of segment level events. And again, a segment level event, it's just a group of two case level events. So that's the way that we detect the correlation between all of them to finally have the cascade. So in that case, if we say the way that we have case level event, if it's different in other data or something like that, we are still did it. But anyway, I think in different type of the data, so we have some kind of case ID. Usually we have this type of ID in the data. And for example, if we don't have a location or something, like we usually have time. And if we don't have a location, we have process or we have different steps or something like that. So it's somehow we should start to changing the context. I think the method can work, but it's just the changing of the context of the location to process or different type of based on the data. Yeah.
Before we move to the question by Bart, David, could you unmute Dirk? As one of the co-authors, he may want to add something.
Yeah.
Yes, thank you. Matthias, just a follow-up question. Did you ask whether we actually could apply this also if the case level events did not have a case identifier in the first place?
I was thinking what is the importance of this notion of a case is indeed, right? Yeah. Whether it would make sense to also apply this to different notions of a case identifier, or whether this partitioning may also be something that you detect actually by correlation analysis, as you would do it in this, or similar, maybe not equivalent, but similar to what you do in the second step, right?
Yes. So very briefly, we need the case identifier to build these segment level events. So in that sense, we actually do not need a case identifier here. We just need enough information to know that two directly following events belong to each other. So if you there have enough information from spatial-temporal context to do that, you don't need a case level identifier. That's correct.
Yeah.
All right, thank you. So then there was a question in the chat by Bart Holmes, whether these techniques and the patterns are also applicable to detect other kinds of performance issues, more like in traditional business processes, and that more to clarify that, what other kinds of patterns can you imagine that would affect performance in these systems? I assume luggage bags, for instance, don't overtake each other, whereas cases in business processes may do that.
Yeah.
Right, so.
Yeah, yeah. Yeah, that's actually a correct assumption. Yeah, they cannot move together. But for example, in the baggage handling system, we can have also different type of system level events which can occur the performance of the system. For example, if one has a problem. It also can be different type of the system level event, which is in our future work to add also to find other type of system level events that can have affect the pattern and also the performance of the system. And if we say in other type of the data, so yes, I think, for example, if we imagine, for example, traffic detection, this type of methods. Also, it also can be something like this baggage handling system. So we can have again different type of system level events, and usually this system level event can affect each other and can be related to each other. But yeah, I hope it answered the question.
Well, if not, I suggest to, well, move this. Yeah, normally take it offline, you would say, but in these days of online conferences, I'm not sure whether that still works. But anyway, thank you very much for, well, the presentation. Thanks for the questions. Thanks for Sarah for answering them. And so let's move on to the next. Yes, indeed, to the next paper. The next work, which is about identifying and reducing errors in remaining time prediction due to intercase dynamics. And that one will be presented by Eva, who is also with the Technical University in Eindhoven.
Yes, I will share my screen. You can all see it.
Yes, thank you.
Okay, great. Well, hello everyone. My name is Eva Klein and I'll be presenting the work of myself and Dirk, which is on identifying and reducing errors in remaining time prediction due to intercase dynamics. And for this, I want to start out with Bob. Bob is visiting the ICPM conference in Padua and he parked his car next to the conference venue, unaware of a forbidden parking sign. Guess what? Bob gets a ticket. Bob believes that the sign was not sufficiently visible and he sent in an appeal against the fine. Now, a couple of weeks later, he wants to know how long it will take before his case is handled. And in process mining, this is a problem that we solve with remaining time prediction. And in remaining time prediction, we learn a predictive model from already completed cases, and we use this at runtime to predict the remaining time of an uncompleted trace, such as that of Bob. And because we want to have as accurate predictions as possible, the primary concern in remaining time prediction is with creating accurate models. And to evaluate the accuracy of these models, we typically use aggregate error metrics such as the mean absolute percentage error or the mean absolute error. Now, a lot of prediction approaches have been introduced, and recently a very nice benchmark has cross-compared 16 of these approaches on 16 real-life event logs. And here in this table, we can see the accuracies of the best performing method for each log. And we see that for 2 logs, there's an absolute prediction error of almost half a year. And we see percentage errors over 30% for almost all logs, of which 3 even have an error of over 50%. So that's our accuracies. That is the best that we have. So what we want to do here is explain the nature of these prediction errors. And we want to do this by qualitatively evaluating these. Then we will use the results of this qualitative evaluation as a starting point to engineer features with which we can reduce these errors. And with these steps, we make a start with establishing an effective feedback loop for systematically improving remaining time prediction. So first up is we want to explain the prediction error. And for this, we have to show 2 things. What actually occurs in the process, the real dynamics, and what we want to predict, and what is actually predicted. And here is how. So we will start with the real dynamics, what actually occurs. And we will do this using the performance spectrum. And the performance spectrum describes how cases transition from activity A to B over a certain time t, which is defined as a segment AB. And whenever in a case activity A is directly followed by B, we observe an occurrence of this segment from time ta to time tb, which is then plotted as a line on the spectrum as follows. Now let's put in a second trace and repeat these steps. And when we do this for an entire log, we get something like the following. So this is the real data. Please notice the batches. This is an example of an intercase dynamic. And we will see in a moment that the prediction model is not able to capture these, resulting in errors. Now, a process consists out of a large amount of activities, and we want to use the performance spectrum to first localize in which steps or segments we find these high prediction errors. And to do that, we will first visualize the real data for a larger amount of segments, which is in this case a selection of the road find process. And here we have colored the lines based on the prediction error of that case in that part of the process, where red indicates a high error and blue indicates a low error. And what we can see here is that the error is highest in the bottom segment, the step from the activity add penalty to send for credit collection, which is also the end of the process. So we see a clear batching pattern and we see that there's high prediction errors. But what's actually going on here? What did the model actually predict? To find out, we will visualize the real data as well as the predicted data. And we will do this using the overlaid performance spectrum. So let's say we make a remaining time prediction for case 1. We fix the time that we make the prediction on top, which is the prediction point in the process. And let's say the actual remaining time is 5. We then plot this as follows. We also have another case, case 2. And case 2 arrives here and has an actual remaining time of 9, which is plotted as follows. And to aid for a good comparison, we extend a line from these points to the bottom. Now, let's say for case 1, the predicted remaining time is 4. We draw a line from the time at the prediction point to the time that the process is predicted to end at the bottom. And if the predicted time for case 2 is, say, 13, we draw as follows. Now, because case 1 was predicted to end earlier than it did, we speak of under prediction, which we indicate with a blue line color. And if a case was over predicted, then we use a red line color. And here is how this looks for that bottom segment of this previous visualization, which is also from the data set that had 180 days of prediction error, the road find log. Please notice again how the cases synchronize in these batching moments. The prediction model does not capture this synchronization of cases. It's actually all over the place. First, we see a lot of cases that should be processed in this batch right here, but actually end up around here. Then here we see cases that should be processed in the same batch, but are actually over-predicted that end up here. We actually even see them mixing up with cases that are under-predicted for the next batch moment. So this is all happening between these batch moments. And then also after the second batch moment, we see a lot of cases that should have been in the second batch and were massively over-predicted. So what I am trying to show here is that this prediction model does not know anything about batching. And now I want to show a way in which we can use these insights to reduce these errors. And we want to do this by giving this prediction model some information about these batches, which we will do by engineering intercase features. Now, we have identified a problematic segment with batching, and in prediction, we have a set of prefixes. And now we want to know for each of these prefixes whether it will be in this segment, which is a next activity prediction problem. We want to know if they will be in a batch, which is a classification problem, and then we want to know how long it will be in the segment, which we will solve using distance to batch prediction. Now, let's say we have a prefix of a case, case 17, and we already know that it will end up in a batch in this segment right here. And what we do in intercase feature engineering is we provide a case with some context of dynamics in other cases by adding this information to the existing features. And we will specifically focus on the intercase context of batching. So this is the feature vector of case 17. These are the standard features used to predict the remaining time. And below is the context of case 17, where on top we see the arrival time within the segment, and below we see the time the case is supposed to be processed in a batch. And this batch processing time, which is yet unknown at the arrival of case 17, is estimated from past values. And now we introduce two types of features that are both an approximation of the distance from this arrival time to this batch processing time. And the first feature we create is the time until batching, TR, where we estimate the time between these moments, which we can then add as an extra feature to the feature vector as follows. And the second feature we create is the batch partition, PN, where we estimate in which part of the batch the case has arrived, which we can also add to the feature vector as follows. Now, we evaluated our approach on two real-life event logs, the roadfind log and the BPI20 log, and we compared performance for these logs with only using the standard features and logs where we additionally use these batch features. And we did this using 18 different remaining time prediction methods. And now we want to recall these prediction errors we saw in the beginning and see how we're doing. And we were able to reduce the error up to 37% for batched cases in the roadfind log and up to 21% for batched cases in the BPI20 log. Now let's look at these errors in a little bit more detail. First up is the highest performance improvement for the BPI20 log. On the left, we have the results of our baseline, and on the right, we have the results of using our batching feature, with on the y-axis the actual outcomes and on the x-axis the predicted outcomes. And now this is what we would like to see, the theoretical best, indicated with the identity line. And on the left, we see a dense cluster of cases that is already centered around this line. And when we look at the same area on the right, we see that the predictions have moved closer towards this line. However, we still see a lot of cases being over and under predicted there. Next, the roadfind log, where on the left we see a cluster of cases that is under predicted. And when we look at the same area on the right, we observe that this cluster has moved closer towards the identity line. Now, again, on the left, we see a lot of cases being over predicted, including a very dense cluster there. And on the right, we see that this dense cluster has moved closer towards this line. And also the other over-predicted cases have moved closer towards the line with a cluster here and an even denser cluster there. However, we still see a lot of under-predicted and over-predicted cases there. Now, we also want to see if the model was actually able to capture this batching. And for this, we also visualize the results in the overlay performance spectrum, where you can see the baseline results on the left and the results of the batching feature on the right. And we can first of all see that the predictions start to converge more towards these batching moments, which is especially the case for the first batch here. We can see that the underpredicted cases have moved closer towards their corresponding batch moments, as well as the overpredicted cases. This also means that this mix of under and overpredicted cases between these batch moments have moved are better separated. And while these are nice improvements, we can still see cases being largely over and underpredicted there. However, what we did show here is that we are able to use insights from a qualitative evaluation, use that to engineer intercase features that, when used, can give a 37% error reduction without making any changes to the prediction model itself. Now, apart from the limitations I already mentioned, our feature engineering method is limited to batching dynamics, and the improvements we get directly depend upon the quality of the engineered feature. And possible points for future work are improving these batching features and exploring intercase dynamics other than batching. However, we think it's even more important when developing a remaining time prediction method that we need to be better in how we do this feedback loop. Thank you for your attention.
Thank you very much. Warm round of applause that unfortunately you cannot hear, but it's there. So we have a couple of questions. So I start with those hands that went up in the participant list. So David, if you could unmute Ricardo, please, then he could pose his question. Ricardo, you now should be able to unmute yourself. Still need to unmute yourself. You are now promoted to speak, but you're still muted. David, could you also promote Arik and Will? So we'll see whoever manages to unmute themselves first. So Arik, could you give it a try? Yes.
Can you hear me?
Yep.
Thank you for the great presentation. I have a question regarding whether we know that this is indeed batching behavior or what we call manual recording. So let's say every Friday, the administrative person records that the case is actually ended. We have that with nurses in hospitals that report that a certain particular part of the case has ended only at the end of the day. So maybe what we need to do here is to change the time scale of the prediction. Instead of trying to predict the exact hour of day, maybe we want to predict at the week's level. Do you think that this is a data issue or more of a real batch processing going on in these event logs? And can we overcome this by changing the time scale of our prediction?
I think that in the case of a hospital, I'm not very familiar with that process, so I don't know about that. I do know that with this process, the batching occurs like roughly 1 year apart, which, well, when changing the time scale, that will be a whole other thing. But so here, I think it's actual batching, batch processing, and we have also seen in other processes, I think this is in the BPI 20 log, that cases are processed on Tuesdays and Thursdays, or Mondays and Thursdays, I don't know, either of those. And I think that there it's maybe more relevant already, this question. But I haven't thought about that in that
taking into account some kind of seasonality, saying that, okay, now I'm trying to predict on a daily or weekly level, and then I will incorporate into my time series prediction model some kind of a seasonality feature that says, well, Tuesdays.
Yes.
Yeah, thanks.
Yeah, that would indeed be interesting, yes.
If a quick question from the chat, could you quickly summarize your motivation to have this partition feature?
Yes, so the motivation is that so we tested different features. So this distance with time, and then also this partition, and for this you used different sizes of partition. And when used for the BPI 20 log, where batching occurs around 3 days, then using this time estimation yielded better performance. And for the road fine log, where batching happens roughly a year apart, then these batching partition yield much better performance. And I think that this is because it's better interpretable for a machine learning model, that these values are not in the thousands, but just like 1 to 10, 1 to 20, around that magnitude.
Okay, thank you. One more question, Will?
Yeah, so can you hear me?
Yeah.
Yes.
Yeah, perfect. So Eva, thanks for the very nice presentation. I think this is an interesting topic. what was not so clear from your presentation, I think there are different types of batching. So there would be the batching where you do things at a fixed point in time. But it could also be that you wait until you have 10 things in the queue and then you do something. Did you use some of these things, or did you just consider, okay, this is somehow a fixed point in time?
I only used what I saw in the performance spectrum, and I am aware that there are different kinds of batching, and I had this question also before already. And yes, I looked in the performance spectrum, and so and there it's it's only what you see there, so it's kind of based on seasonality, I think, and also when predicting these batch moments. We do this based on past values. So there we kind of need this to be seasonal, because if it's not, then if it's arbitrary, we can't predict these batch moments, and then the accuracy will be very off.
Yeah, but it does not need to be arbitrary. It could just be like stock keeping systems that you wait until you have a certain amount of work, and then in one batch you do everything. So perhaps a related question is that in your performance spectrum diagrams, the batching was always very clear, that there was like, it was going to a single point, where I could imagine that batching is not always like that there are periods of inactivity and there are periods of activity. Could you also use your approach for that?
What do you mean by inactivity? That in that segment there's a long time without anything happening?
Well, there could be, let's call it loose batching or something like that. Somebody only works on Friday and he doesn't do everything on Friday at 9 o'clock. There is simply, if something happens, there is a higher likelihood that it happens on Friday rather than another day. So if you would look at the performance spectrum, these things would not go nicely into, let's say, a single point, which seemed to be the case in your examples. Yeah. But these would be more, along the timeline, you would see periods with more activity and periods with less activity.
That's at the moment not really incorporated yet. I have thought about it because with in a previous paper I've kind of detected these batches, and there I also thought about that batches do not end up in a single point in time. They are kind of separated still at the end. And I think when including that, it could also be used in the prediction. But at the moment, that's not included in this work.
Yeah, thank you.
I have to interfere here. Thank you very much, Eva, again, for your presentation, for answering the questions.
Thank you.
There are two more questions related to your talk also in the chat. Maybe you can check them and try to answer directly there. And now we move over to Tobias, who will present the third paper in this session, which is about time-aware concept drift detection using the Earth mover's distance. And after we had an Eindhoven-Aachen paper and an Eindhoven paper, now we have an Aachen paper. So Tobias, please go ahead.
Okay, so can you hear me? And can you see my screen? Okay, then, my name is Tobias, and I'm probably the last person that stands between you and your well-deserved after work hours. And this is going to be the talk about time-aware concept drift detection using the Earth mover's distance. So to start with, why concept drift detection and what is it? So I think that we are interested in concept drift detection in general stems from the following fact, namely that business processes are embedded in a complex environment and thus subjected to continuous changes. On the one hand, this is of course what makes this entire field of process mining so interesting. And it is the reason why we are interested in concept drift, because concept drift is simply detecting these kind of changes. So why do we care about these changes? So on the one hand, this helps us to capture the process dynamics and to follow how the process evolves over time, and therefore understand and generate new knowledge of our process. On the other hand, it also allows us to verify and identify periods of steady behavior, which can then subsequently be used for other process mining techniques. So to motivate our specific work, consider the following example of a fairly general application management process. So we start with registering a case, then there are two concurrent workflows. After this, we consolidate our results, and potentially there will be eventually some fraud detection. Even in this very simple process, there can be multiple different kinds of drifts. So the first drift, of course, control flow drift, namely in this case, changing from concurrent behavior to an OR relation. This is probably the work or the kind of drift that most of the work until now is focused on. But as you see from the description of the current session, there's more than just control flow. And from the title, you know, well, time is probably one thing that's the main driver for processes. And so let's add time to this drift detection scenario. So having time, there can be also multiple drifts. Of course, there can be a drift, for example, with service times, also journ times, but there can also be drifts that require both perspectives, namely control flow and time. So in these kind of holistic drifts. So consider our fraud detection activity, which due to resource limitations, we can only execute it like for 15% of all our traces. And now which traces to or which cases to select. So a very good proxy for this is, of course, the difficulty, and here the proxy time. So a long time for example, for consolidation is probably a good hint that this is a very difficult trace. And if there are now adaptions based on, well, more difficult cases, there's the higher likelihood that there will be fraud. So we should investigate these. These kind of drifts require a holistic drift detection framework. And this is also our contribution. So the problem statement is, well, there's more than just control flow. And what we propose is a step towards a more holistic drift detection. We do this by proposing a framework that's based on the earthmover's distance. Using this framework, we are able to, on the one hand, identify control flow drifts, and on the other hand, time drifts, such as time and control flow drifts, or even extend our framework, although this is beyond the current work. So for a quick overview, the references for this work, and actually to make the point for the previous slides, 4 of these works only focus on control flow. So what's our approach? So in general, we will apply some sliding window fashion, sliding a window over our log. From this window, we're going to represent sub-windows left and right using stochastic languages, where we enable also to incorporate additional perspectives in our stochastic window representation. Next, we will define a measure that kind of verifies or gives a value to how how similar different traces are. Based on this trace distance computation, we can then finally apply the EMD to detect drifts visually. So let's start with the very simple case, only control flow drifts. So here we will use an alphabet, which is simply an alphabet over activity names. We will use general event logs, which are just a multi-set over this language. And our window representation will be by means of stochastic languages, which is simply a probability distribution over words over our alphabet. So for example, in our example here, we have register, workflow 1, and consolidation with very high likelihood and a very low likelihood for the second trace. These two together form a stochastic language. So as mentioned before, we need some way to compare different trace variants from our stochastic languages. And therefore, we will introduce some trace distance function, which is simply a similarity measure of trace descriptors. And ideally, we also want it maybe to be a metric, although this cannot be ensured in all cases, but it gives a nice interpretability of the distance function. So for a control flow, what can be used is, for example, the Levenstein distance, or in this case, normalized Levenstein distance. So, and this is where we are at this point. So we have on each side distribution over trace variants, and we know, well, for each variant, how to compare to a variant of the other window, and what's the similarity between these two. But how to compare the entire distributions with each other. And this is where the term or our EMD comes in. So the EMD can be formulated by the following linear program, but the general idea behind this is, well, we have the distribution on one side, distribution on the other side. This side will be represented as a set of piles of earth, and on the other hand side, we have the holes. And now the EMD describes the effort to transfer all our earth from the hills into the holes. And the effort that's taken for transferring a single unit of earth from a hill to a hole is described by our trace distance function. So what we want to do is minimize the flow over the flow with respect to our trace distance function, and we have constraints simply stating that on the source side, so every hill should be completely transferred somewhere, and also every hole should be filled. So this is a very nice probability distribution, similarity measure, and it very well matches the human perception, as has been shown in previous work, especially from the field of image retrieval. So here's an example how this can work. We have 3 traces on each side, and here is depicted the possible flows with the cost on the right and the actual flow and the optimal solution. So in this case, for example, we can transfer all the probability mass from this trace to actually itself because it's present to the same extent in both windows. But also, for example, for this case, it's not present in the second window, so it's only limitedly present in the second window, but we also have to move some of its probability mass to a close variant in the other window, as can be seen here. So this will then give us some costs and actually will be a notion of the difference between the 2 probability distributions. So as promised before, we also want to incorporate time because it's the main driver of processes. So how to add, or be more general, how to add additional perspectives. And there's a very straightforward approach, namely, well, we start with extending our alphabet. So we have the alphabet of our activity names, and we will extend it by a view alphabet with somehow an additional descriptor that can be used. In the case of time, what we did is just apply binning to, for example, the sojourn times or the service times of activities. This then gives us a view alphabet of simply the bin index that we found with our binning approach. The next thing that we need is a trace-aware distance. So for finding a time-aware distance, we will propose the following, namely to build up on the weighted Levenstein distance, which then incorporates control flow costs and time costs just as a sum of them. So how does it work? To see this, consider the following 2 traces and see how renaming would work in for these 2 variants. So we can simply start with our registration, which has the same time. So it's an easy match, no costs at all. So now we have workflow 2 and workflow 1. So we will need some renaming activity costs, and we will also add some time difference costs for some technical reasons that might become clearer on the next slide. Then we have different, or what's not really in the general Levenstein distance as well, we have matching because activity names match, namely consolidation in both traces, but times differ. So we have no costs for matching the activities, but we will have costs for the time difference. And then finally, we'll have to delete the fraud detection because it's not present in the second trace, and this will give us some general activity deletion costs as well as time deletion costs because it should be more expensive to delete very long-lasting activities than maybe the short-lasting activities. So as described more general before, but now we want to have a better prioritization. So how can we fix these kind of costs so that they work? So in order to make them work, we also want to fulfill some interpretability axioms. In our case, we want to, first of all, achieve that in general, renaming should be preferable over just, deleting it in the first trace and just inserting the other event from the second trace in our trace, although renaming could have been applied. Also, if you have two different events which have the same activity level but a quite large time difference, we want that matching them is, of course, again, less expensive than just deleting the first event and inserting the other. And if we consider 2 events that have the same time difference and different activities, then renaming these 2 should in general also be more expensive than this kind of matching. To achieve this, or one can achieve this rather easily, simply by choosing fixed costs for control flow renaming or control flow deletion. And with respect to time, if we delete it, then we will simply take costs linear in our bin index, or if there are 2 times involved for renaming or matching, then we can use the absolute bin difference. So, and this is where we stand now. So we have time-aware representations on both sides, and we know how to compare them individually. So what to do, and this is what's quite nice about this approach, well, we can simply again apply EMD. There are no really additional requirements, and so in choosing our representation and in our distance, we are kind of free to incorporate time, and maybe also free to incorporate time differently, also incorporate other resources if we find the representation and the distance. So how did we evaluate? So for our evaluation, we built up on an artificial data set that has been derived from a model that has already been used for concept drift detection. And on this model, we are able to identify the control flow drifts that have already been introduced in this work, as well as long-term dependency drifts, since we always consider the complete trace in our representation. But for this presentation, we will just focus on one aspect, namely the time aspect. So two examples for time drift. So the first example will be a kind of sojourn time drift. So what we did here is, well, we start with baseline inter-arrival time, then we increased the inter-arrival time, went back to baseline, followed by 2 steps of decreasing our inter-arrival time with a decrease on different order of magnitudes. So what we also did is we removed these kind of dashed activity here because due to the sojourn time drift that has been introduced, we would also see a control flow drift if we would leave them in. So this is just to ensure that there only will be a sojourn time drift. And this is kind of what our result would look like. So we've implemented this method as a plugin in PROM, and we have like 2 plots. And to complete this complete research track, we'll also use the word spectrum here. So we have a spectrum of a process. In this case, we'll have different window sizes, and using this kind of spectrum enables us to do 2 things. So first of all, we could find drifts on different scales, as in general should be done or using spectrums. And we can also use it to somehow verify if we have an indicator of drift on a small scale, to verify it on a larger scale, because having bigger windows allows us to incorporate more information from the probability distributions. So what we can see, and what's quite nice, is that we have a measure of impact of drifts that also shows the effect. So for example, we can see that just increasing the inter-arrival time did not really cause stress on the process. So everything works smoothly again. So there's no real drift or no real significant drift detected, but we see significant drifts for each of the decrease, and we have a measure of effect. So for a smaller decrease of the inter-arrival time, we detect a small drift, but here the larger drift here. What you can also see is somehow this nice kind of linear development here, which can be attributed to the fact that 2 facts. On the one hand side, well, the drift sojourn times become larger and larger and larger because of the stress, and also because in general operations here become more expensive, because if you now delete a certain event, it's very likely that we have high time costs. The second drift that I teased at the beginning is the type of drift that we can only see when we consider both perspectives. And this kind of drift also kind of nicely shows to some extent the limitations of our work. Limitations of our work. So what we did is we used time as a proxy for difficulty, and we now introduce the relation between this activity and whether we later on call the claimant or not. And if we also focus on this kind of lines of the low insurance check and the notification, then we can see the drift that has been introduced in this case, although it's not as significant as before. And what this kind of nicely shows us, that our framework kind of knows us to have multi-perspective drift detection, although here it requires a rather large window and also like a small zoom in onto the process. Which brings me to my conclusion. So what we did is we proposed an EMD-based concept drift detection approach that enables multi-perspective drift detection. We illustrated how to incorporate time, but other perspectives may also be incorporated. And we try to evaluate on different time of drift as well as control flow, but here only shown time drifts. For future work, of course, evaluation on a real-world data set would be nice, but it's always kind of the problem that is there with concept drift detection, having a ground truth on real-world data, then investigate additional trace descriptor and distances for other perspectives or to be more concurrency robust. And then, as we've seen before, this zoom in well, that would be nice to have a good methodology to find the best focus. Of course, event stream can be interesting, but what I think is first and foremost will be interesting are diagnostics to really see what has happened in our drift. And that's it from my side.
Thank you very much. Thank you. So let me start with one question from the chat. No, that was related to the previous talk, so I will not pose that to you. Are there questions? So we are a bit at the end of that session, but nevertheless, there would be time, let's say, for one or two quick questions. Now everybody's really waiting for me to close the session, but I will not do so before I ask Tobias at least one small question. You somehow mentioned it a bit. I mean, time is of course an important perspective, and I see how this whole framework can also be applied now to different resources. It's not intended to be a mean question, but in practice, drift detection is easy when we know what to look for. So how would you say, or how would you apply this, right, in terms of all the different perspectives that can matter here for drift detection, right? How would you go about it? More like thinking maybe a bit in terms of a method, a methodology. So yes, time is probably important. You mentioned there are other perspectives as well, probably considered as future work. How would you go about that?
So actually, well, the easy way out would just to say, well, if you give me enough data, I can somehow detect everything. But this is somehow the major problem that we are facing. So the well-known curse of dimensionality, if you incorporate more and more descriptors and more perspectives, actually the number of traces that we need in each window kind of explodes. So what would be, for example, one way is, well, we can have on the one hand side different perspectives and also different parts of the log. So doing some kind of, well, we maybe do random projections, see whether we can find drifts on this, maybe also extend once we find a certain drift, see whether we can extend it or look something else. I think this is also somehow a similar approach that has been done, some work of comparison where they just had the features, selected a random subset of features and then try to see whether this works on. So the similar approach could also work in our case, I think.